Mark, I have a question real quick. Is
Oh,
that
sure.
a two-phase type of instrumentation?
What are you asking about?
Like, is it two sine waves going in on each other? Like, since you got two different directions going.
Are you talking about the chart that I have above me?
Yeah, yeah,
Oh, those are not waves. Those are well, they kind of are waves. Those are movements in this entire rig. Like if I move it like
yeah.
this, you know, if I move this around, you see that these are force sensors over here, two force sensors giving me the X and the Y of its movement.
Okay, I see. Okay.
So
No,
really, we're just concerned with the Y. I just wanted to see if there was anything happening on the X. Nothing's really happened. Oh, actually, no, this is the Y. This would be the X. So we're really only concerned with the X movement, the left and right in this configuration, because it's expected to move in this direction. This direction was here just because you need something that, you know, to stabilize it, and we had an extra force sensor.
yeah. And so, like, what's the limit though? How far it can go before it starts clipping? I guess as far as like distortion wise.
Um, they're uh, they're able to go up to 10 newtons of force, which is about a newton of force is 100 grams. That would be yeah, like a couple pounds of thrust before it would start going over the edge. There's a switch that allows you to go to 50 newtons. So this is on the sensitive setting, right?
Yeah, yeah. But that's good that just fine tune it more slowly and get it up there.
Right. Well, what we're actually fine tuning is there's a chip board over here that it's sort of like a robotic chip for
Yeah,
robots with PWM.
yeah.
And Tom over here has been programming it, working with the people at Palolo, right? Mm-hmm. Yeah. So it's really just changing the settings on that. That's what we mean by programming, and then we'll power it up on this apparatus and see whether it created more thrust or less thrust, and what we're looking at.
All right.
Mark.
Hey, Mark? Mark?
Yeah, go ahead.
Hi.
Both of them.
If
the
I
rotor
understand
were forward.
your graph, the blue lines above the zero axis is going away from the camera and below is going toward the camera.
The blue line is
Yeah. Mark, if I could jump in. So, I think this was some of the confusion. So you've got the blue and red. One of those is sideways, right? One of those is like your y-axis. And then one of those is front to back. That's the x-axis. And that's where you're expecting to see the motion. So
right.
One of them's lateral, it's side to side, and maybe something happens, right? Because it's shaking. And then the other one is forward to back.
Exactly. And I'm gonna see if I can zoom in over here onto the
Okay, so you're just trying to make it less sporadic.
So the red represents side to side then.
Yeah, I see. That's cool.
Right, Mark?
I'm understanding this. Like, this is pretty cool. So it's just fine tuning. You're just trying to get a bit smoother curve. So.
Yep, pretty much.
I'm gonna do the same attempt with a cell phone. I'm gonna try. I want to start at 1 hertz.
What are you working on?
Like the same thing, kind of like similar to what you're doing, like with just fine, tuning the curves and stuff. But I want to use like the cell phone at a very low vibration, like 1 hertz, and then I'm gonna try to see if I can have some measurement scheme of detecting any like a wattage meter or some similar deal, and just try to use less wattage possible to get to a higher frequency. So, but I'm gonna try to start off at a very, very low type thing. But like all I'm doing right now is extra reading on it. So, I'm kind of new to this, but it seems pretty simple a little bit. It doesn't seem too hard. It's like X and Y axis, right? On a circle line, you got your degrees that it's rotating, and those angles are the fine tune, and you just gotta match all the phases right, different time variations, and this is very fascinating. So, and this is why I didn't really care for cash. So I hope you understand what I'm getting. I'm pretty sure.
No, I really don't.
Oh. Well, you know,
So
you got
Mark,
like, go ahead. Let's hear it. I'll just,
oh,
you know.
go ahead. You say you're not concerned about the red. That has no bearing on your goal for this experiment.
Yeah,
I asked why.
the red measurement is, in this case, it would be the y-axis. We're only expecting movement on the x. So
Okay.
if I found a way to remove it from the chart, probably should try doing that.
So you just allow just a free move on all axes parallel to the floor or the surface of the table.
Yeah.
I think it's interesting. You have significant lines in the red, even more than the blue.
That was just from us. Yeah, I think I was adjusting it manually.
Oh, you're adjusting it. Okay. All right. Thanks.
Yeah.
Mark, Harold, if I have a question. If both of the arms were pointing forward in the same direction, and looking from your side, let's say they were both spinning in the same direction, let's say counterclockwise, how much force do you expect to be producing? You know, they were just pointing forward, stationary, just only the wheel spinning. How much gyroscopic force do you expect that will be producing, let's say, toward the X direction?
I don't really know. This was based off of Mike Gamble's concepts that he talked about several times at APEC. So he said that it works best with up to 15 degrees of movement, and that at a certain point there's a lower return on investment. Like you don't really get much more effect by going any farther than that. So that's really what we're sticking with. This is basically at its core what it's supposed to be is a angular momentum device that converts angular momentum into linear motion. So it's supposed to go against the conservation of angular momentum and find a way to cheat that through complex pulse spins.
Yeah, that's what I'm doing with trying to do with the cell phone is, you know, fine tune the angular momentum where it doesn't, you know, clip in the signal. You know, if you're doing like Fourier analysis, like on an oscilloscope, so like, you know, you're trying to use less energy or wattage. That I was just trying to tell you what I was trying to get across, like, say, you know.
Yeah. Well, guys, so let's go to open discussion. You want to do that?
Sure. This is the relevant data, by the way, from the x-axis, and you can see right over here between the two ones. That's the 0 point. So there is more thrust in one direction than the other, but there is a little bit of a return pulse. I also posted a video on YouTube showing this device scooting across the table on a similar platform of ping pong balls, and it was just able to swim around. It was pretty cool. It's a little scary when it's up and running because these rotors over here have a lot of angular momentum to them. If they come in contact with flesh and bone, they can be pretty nasty. And we've had one gouge out a wooden table before when it fell over. So we try to have something handy to remove that energy from it. So we're in open discussion. Anyone can.
So Mark, it looks like you have more spikes in the opposite direction, but larger spikes in the direction toward the camera. Is that correct?
Yeah. So I just changed, guys, if I could jump in real quick. I just set it, I removed the spotlight from you, Mark. So, I mean, you keep talking about this, it's totally cool. But so now it'll show Robert when he's asking questions and all that. less
All
stuff.
right.
Oh, okay, so you're gonna, yeah, Robert, you're gonna have to look at the screen again. Yeah, there is, in terms of number of spikes, I'm not sure that there's more of them in the opposite direction, but there's definitely bigger magnitude and bigger overall energy, force in the negative side of the scale, which is, it seems where we're seeing that forward momentum.
I
It'd be
noticed
interesting doing a general energy analysis to see if there's more energy going toward one way than the other.
I've always noticed that though in a lot of vibration analysis systems using they would test on just different objects that for some reason that this graph line would always go to the right when it gets up there near like past the megahertz range a bit. For some reason it always veers off to the right. I don't know if that's any relevant what I'm trying to I mean, like I said, I'm new to this. So I don't know all of this all the way. I'm studying.
This is gyroscope propulsion. You're probably talking about some RF stuff.
Yeah, but it's the same thing. It's mechanical resonance. It's all the same, thing. I mean, it's just how the model of physics I follow is just mechanical resonance, and it's just that electricity, infrared, UV light, gamma rays, and the whole EM spectrum is just all the same thing. It's just the more more pulse rates you go, the more that the energy transforms into whatever phases. So. Oh, hold on.
Hey, David, how are you?
Oh, sorry, I had to do something, but go ahead.
Oh, me? I'm
Yes,
fine.
David, how's it going?
Oh, it's going great. I know I've been absent from the discussions for a long time, but I'm glad to hear things are moving forward on recreating the 1994 experiments.
Yeah, you probably have to watch a couple of the past updates that I've done on it. I promised you that we'll run the experiment and we'll stick enough energy into that waveguide that if we don't see weight loss, we'll burn it, and we did. Yeah, we had a sample go up in flames, and then we added temperature sensors to the box, and I mean, it's a much more sophisticated setup right now with a lot of different variations to the setup that we've added. And we've seen our best results have been with really thin film aluminum.
Thin film aluminum meaning what? A sample that weighs very little is?
Yeah, it weighs very little. Like the Mylar aluminum emergency blankets that the Red Cross uses. It's very thin aluminum layers, and RF is able to penetrate that.
Do you know that as long as you're able to induce dynamic nuclear orientation in that thin layer, whatever is in contact with it should experience a transference of dynamic nuclear orientation from that layer?
Right. So what I did was I put a little pebble of osmium, which is the densest metal in existence, and surrounded it with that aluminum foil stuff. And we saw some weight loss, and it was precisely at the 28.025 gigahertz per Tesla. Right when we reached that sweet spot, we saw some movement and a little bit of weight loss. You got to replicate that experiment again. We were using an analog scale at the time, and the problem with the analog scale is that when you see the weight loss, it's moving, and if the sample's moving, it's losing its sweet spot already. It's losing that little spot at the center of the magnet. So we're going to replicate that experiment with a digital scale, so you don't have that much of a movement issue.
What was the pulse width in that experiment?
I shifted it around, but it was somewhere around like between 2 and 10 milliseconds.
Yeah, okay. In the 1994 experiment, you had a completely different frequency, and you had a longer pulse width. And I was wondering if your pulse width would shrink as you went to a lower frequency. But, you know, you have the ability to, you know, push it around and see where it seems to work.
That's what we're gonna do.
Of course. Well, so you have the Tesla conference coming up, and then afterwards, perhaps you'll be going back to the Alzaphon effect, as you call it.
Well, we're gonna work on it again in a little bit. Right now, it's April 23rd. The Tesla conference is at the end of August, so we got a couple months until then. It's in Albuquerque, New Mexico. If you'd like to join us, that's Tesla Tech in Albuquerque, New Mexico. It's hosted by Steve, I forgot his last name. Really nice guy. We've been there last year. Tim Ventura is probably going to be joining us. I'm going to be presenting there as well on the latest research. And from all the conferences I've been to, I really like this one. I think it would be a good choice for you, David, if you wanted to come down and meet some cool people. And it's not just going to be Alzaphon. There's a couple other experiments going on there. And
I
you know,
wouldn't
they
expect
have
otherwise.
a water powered car, you know, free energy devices, great
Yes.
food, great company. It's really nice. And it's not too expensive either.
Sounds great. We'll see. I don't, it's all new.
Hey, Mark, do you have a link for the conference?
Yes, Tesla Tech. Tesla Tech. Let me just do a Google search.
Tesla Tech is usually
Yeah.
August. It's usually the end of August, beginning of July, or sorry, end of July, beginning of August.
I
Like
thought it was more like the end of August or middle August.
He might have changed it,
Yeah.
but
Yeah, but like I said, Mark, I think your experiment is probably near the best approach to get to like anti-gravitic effects. What I'm trying to do is like you have your dot on a circle and it's going around, you know, you have that like one rotation depending on the degrees, right? And the more like the different angles you have, like say you picture you have your sine wave going up and down, and then it kind of like it goes up like a curve. You would measure a curve, you know, going up, and it would, you know, the sine waves would go up that curve, and depending on the angles, you know, that you would have a straight line drawn through those sine waves, like that would actually determine the phase alignment, and that would make it more energy efficient. That would allow you to like line up all the amplitudes, you know, correctly. You know, like that measurement would determine you know, the phase alignment better. You know, depending on like the angles that the point is at. Like say you would have your 2 points. You would have one point that's going around, and that's your pulse rate, right? The dot on the circle, and, you know, just mathematic wise, you know, and the faster it goes, the more, you know, more frequency you have, you know, just using one sine wave as an example. And then you have another point on the circle, and that point doesn't move. That point will help you draw a straight line through the you know, through the sine wave curve, and like you're trying to see like, you know, angle measure out where all the theoretically where all the wave crest, you know, the dang it, what do they call it? Crest and troughs meet, you know, exactly in phase. So that would make your less energy requirement needed. You know, you wouldn't have to jam, you know, like 1,000 watts until you just get a high frequency, you know, if you catch what I'm trying to say.
No, I don't catch what you're trying to say in relation to this mechanical device, which can only be discussed in terms of RPM and angles of movement.
That is, but no, that what I just said is angles of movement. It's RPM, and it's just
Yeah.
like you're
I
studying.
mean, the frequencies that this is moving back and forth are very low there.
Yeah, but it's the same concept. It's really the same thing. Like you said, angular momentum. You know, angles on a circle. You know, it's, you know, the dot is spinning around, so that's, you know, literally the same concept. I mean, I'm just saying what you're doing is like what I'm trying to do, but I'm using, you know, like a math scheme. This isn't, you know, alternating current measurements in like, you know, regular circuit boards and stuff. You know, the same thing, a lingo the electricians use. So, you know, like using that circle measurement phasing would determine better energy efficiency. So, you know, you would require less power to get to a higher frequency. So I don't know if that helped. The study of angles, you know, on measurement line for, you know, phase alignment. So you should really check it out. You know, that's just the research I've been digging up. So
When
So
you have
Mark,
any-
you talk
Oh,
about,
Go ahead, Robert.
Steve Ellswick.
Yeah, that's Steve Ellswick at Tesla Tech. So
I spoke with him several times. I
Yeah,
feel
he-
sorry for him. He lost his business partner several months ago or last year. So he's
Great
doing it
guy.
on his own.
He's doing it mid-August, so it's August 10th till the 14th. So if you can make
Yes.
it there,
Yeah. I don't think I'll make it.
register before May 31st, and you'll get 25% off.
Yes, I know that. Yeah, I know, but still, I may not be able to make it. I got so
Okay.
many other things going. Life happens, but
Guys, take
I'm
care.
hoping to visit your lab fairly
We'll
soon.
love that. I gotta run,
Right.
guys.
well, it was nice talking to you, Mark, man.
Take care,
Good
Jeremy.
to help out. Yeah.
Yeah, I think we're actually kind of winding down for this evening. Yeah, so you know what? Why don't I stop recording now? I'll do that, and I mean, so let me do that. I will stop recording for this evening.